Hi there and welcome to Workshop 3. So today we're going to be looking at assessing the distribution of a numeric variable. And so the key things that we're wanting to do when we assess a numeric variable is essentially give an idea as to where most of the values lie, so a measure of the centre or the typical values that the measure takes across all the data, the kind of the range or the spread of the data, and also the shape of the data. So are the measures distributed symmetrically around the centre, or are they kind of to one end or the other? Is there some skewness there or anything like that? So we're going to look at the Quake starter again. Let me run all this so we can get the first histogram up. And so a histogram is essentially where we divide the data up into small buckets or bins. So we divide the range of the magnitude, which varies from 4 up to 6.5, up into small segments. So maybe it's, say 3.8 to 4.2 and 4.2 to 4.6 and so on and so forth. And then once we've divided that range up, we count the number of observations in each of those bins. And then we plot that vertically. Okay, so the histogram, the geom histogram layer here automatically divides the data up, counts the number of data points in each one, and uses that to derive the vertical axis, the count axis here. So the idea is that it gives you a shape, and where the graph is highest, that tends to be where typical values are. So most of the values are kind of between 4 and 5 here. That's kind of the measure of centre. The spread is between 4 and 6.5. That's the range. And you can see that it's not symmetric, so most of the values are actually small, and only a few values are large. So only a few earthquakes have that very large magnitude, so you get this kind of skew distribution. Okay, skew to the right slightly. So perhaps let's write a little bit about that. So when I talk about skew to the right here, I'm saying that there's a small number of or the kind of the long tail of the data is out towards the right, which means that most of the data is on the left. So skew right means most of your data is on the left and the long tail is to the right. Skew left would be the other way round, where most of the data would be to the right and the long tail is to the left. Typically, skew left data is not something that happens very often. Most data is kind of ends up being skewed to the right, and that the extreme values tend to be larger rather than smaller. Okay. And so by default, you can see down here that it's picked bins equals 30, and it's suggesting that we pick a better value using either bin width or bins. So we can change the number of bins that we want. So 30 bins is the default. So that's basically 30 bars here. We can change that with bins, and so that's just specifying bins inside the geom histogram, but of course outside the mapping piece. So bins equals, say, 10. Let's do that. And you can see that you generally get the same shape, right? You can still see the middle is again down between 4 and 5. It's left, it's right skew, the same as it was before, but it's kind of a little bit chunkier, right? Because we've partitioned it into fewer bins, so each of the bins are larger. So Same conclusion from this plot, but the display looks coarser. The chunkiness of the plot is very apparent. Right, it's basically less smooth. If we increase the number of bins, let's say 15, let's try that. Then we get that, and so you've got more bins, 20. And you notice that as we change the number of bins here, things are actually very different, right? The plot you get is quite different. So you can see here with 15 bins, we've actually got kind of these little dips. And so we kind of lead to the, it leads us to question, does the data just have a single peak here, or is there actually 3 peaks there? And we can see that the conclusion changes quite a bit when we go from 15 to 16. It's like, well, the place where these peaks change is quite different. So with these data, the number of bins makes the plot look quite different. And the reason is that the data here are rounded, right? And if we have a look at the quakes data, if we have a look at the magnitude data, you can see that it's rounded to the nearest 0.1. And when your data are rounded, then that means that there's no data between 4.0 and 4.1. The quakes are either at 4.0 or they're at 4.1 or higher. There's nothing at 4.05 or 4.03 or anything like that, right? So when you're dividing the range of data up into bins, where the data falls is quite important to the shape that's going to result. And so you can kind of demonstrate that by basically showing where the data lies. So perhaps we'll try and achieve this. Maybe we'll use a rug. So a rug places the make it red maybe, places the actual location of the points along the x-axis. Right, so this is where the data lie, and you can see that there's no data in between these gaps here. Right, so if I make it obvious where the bins are by perhaps let's make them transparent. Oh, makes them disappear. We'll make the outside of them visible. Okay, so there we go. So you can see here that the bins that are higher, like this one here and this one here, are because there's actually 2 different unique values in the data, right? 4.3 and 4.4 both contribute to that bin, whereas the bin in between them, which is shorter, only 4.5. So only the single value 4.5 contributes to that bin. And again, this other tall one, there's 2 contribute. The short one, there's 1 contribute. The tall one, there's 2 contribute, and so on. So that's why you're getting that kind of repeated pattern of every second bar being taller. Let's maybe actually just perhaps what we could do is actually make it. We'll leave the fill, but maybe just change it to be a little bit transparent with alpha equals say 0.2. That's better. Right, and it's the same when we change the number of bins. So if you look at 20, then it's quite extreme, right? So you've got this, these few spikes here, and that's not actually reflective of what the shape of the distribution is. Just a matter of the fact that we've got in that particular bucket or bin, starts just before 4.5 and finishes just after 4.6. So you've got the 4.5 and the 4.6 quakes in the same bucket, if you like, and the same with this little spike here. So these are just artifacts of the number of bins we've used, and if we change the number of bins slightly, we're going to change where those happen, and so you get a different shape. And so that's why when we looked at the original plot, we had these gaps. So in the original plot with 30 bins, we had these gaps every now and then. That's just because the gap, the bin fell where there's no data, right? So this bin here, where there's a big gap, is exactly in between where the actual data are. So thus there's no data in that bin, so the count of the values in that bin is 0, and so you get that weird behavior. So when your data are rounded like that, you've got to be quite careful with your choice of bins. And one way to do that is to, instead of specifying the number of bins, we could specify the bin width. Okay, so let's put the examples here just so that we can see them. So this one here, that's e.g. the tool spike. Let's do bins equals 30. So an alternative is to specify the bin width and then the start of the bin. Right, so because we know the data is rounded to every 0.1, what we could do when we create a histogram is we could say, instead of saying we want 30 bins and have the histogram work out where those bins should be, we could instead say that the bin width is, say, 0.2, right, so that we know that the bin will capture every second observation, and maybe have the boundary at 0.05, right, so 0.05 would be halfway in between, right? So like 4.05 would be halfway in between the two data points. And when we do that, every bin now contains 2 data points, except the first because we're at the end, right? Contains at least 2 values, and so we get a nice smooth distribution. Okay, and similarly we could, we could basically, change the bin width to be 0.1, and that would give the same effect, right? Many more bins, but you get that same smoothness. And the reason you get the smoothness and no odd spikiness is because we've ensured that we don't have that situation where we get 2 separate x values contributing to the same bin to make it extra tall, or no x values contributing to make it extra short or whatever. Okay, so that's the histogram. And again, you can see that, the center is at about 4.5. That's where the mode of the distribution is, the most common value. Most of the values are between 4 and 5. It's skewed to the left in that most of the values are on the left of the skewed to the right in that most of the values are on the left of the plot. We get a long tail to the right. And the spread is from about 4 to 6.5. So what about other plots? So there's a couple of other ones that we can use. So the density plot is my favorite. So the density plot essentially gets rid of some of the problems with the histogram. It can be thought of as a smooth histogram. Okay, so we just take the same code we had before, and I'm just going to change it, get rid of all the extra guff. I don't need any of that anymore, and we'll just switch to density. Okay, and so essentially it's like it smooths over the shape that we have there in a smooth line. Okay, and it does that in the same way that geom density 2D is. Essentially what it does is that you've got each of your observations. So let's put the rug back on so we can see that as well. Copy and paste it from there. So at each of these little points where we have data, it puts a little blob, sort of a little blob of jelly, if you like, around the point. And where the observations are similar, in this case they're exactly the same, those blobs of jelly will add up. on top of each other, and so we'll get it like a very tall piece of jelly, and then they're going to spill over a little bit between observations. And so in the end, because most of our observations are down here, we get a big mountain of jelly down here, and that kind of shows you where the shape is. You can see the small bump here is because we've got observations around 6, but we don't have one at 5.8 or 6.2 or 6.3. Okay, which is why you get that little hump down the bottom there. Okay, so that's the density plot, and it's kind of what I prefer, I think, to the histogram in general, because it doesn't have those problems of, it doesn't matter that the data are rounded quite so much, because it's, smoothing across everything. And so you don't have those, bin width problems. Nonetheless, you can change the amount of smoothness. With the adjust parameter, so if I specify adjust less than 1, say bigger than 1 first, let's make it 4. So adjust greater than 1 smooths more. Right, so you can see here that we've smoothed out a lot of the distribution, and instead of getting that nice, that indication that it drops off quite sharply, we've smoothed it over a lot, and so we don't get that quite so much. Okay, and so this is probably over smooth. The data doesn't really look like this. It's just we forced it to smooth more, and so it's it's done its thing. And we can also smooth it less. And when we smooth it less, we potentially hit that problem with the spiky nature of the data, right? So if I smooth it less with an adjust value less than 1, then you can kind of see where those mounds of jelly, individual mounds of jelly are, right? They're all spikes are on the observations, and so you can get a sense of how it's actually producing the plot, right? Clearly this is way too undersmoothed, way too noisy. So if I increase it a little bit, increase the adjust a little bit. Whoops, somehow I put it in quotes then. So maybe 0.6. Right, so you can start to see, that it's smoothing less, but we're still probably under smoothing here. There's a lot of kind of little changes in direction that probably aren't actually true to the data. Okay, so. So typically the default, which is adjust equals 1, works well for most data sets. Okay, so that's the density. You can change it a little bit with, so the things you can change on the density plot are the color. So you could change it to green, say. Okay, oh, that's a horrid green, maybe dark green. There we go, change it to dark green. That would change the color of the line, and you can also fill it. So you can say fill equals, say, pink. This will perhaps not look the best, but you get the idea, right? So you can fill the underside. And I quite like doing that, particularly if you add some transparency to it. So, make it a little bit coloured, but add a little bit of transparency so you can still kind of see the grid bars underneath, which can help, show you where centre is and things like that. Obviously, you probably don't want to combine green and pink together necessarily, but you get the idea. And so the last one that we can use is the box plot. Right, so the box plot, let's get rid of the rug. So the box plot plots the minimum lower quartile, median, upper quartile, and maximum. Okay, so this is the 5-number summary. We'll talk about we'll talk a little bit about this in lecture 3 on Thursday. Okay, so the the point down the end of this line here is the minimum, so that's 4.0. The maximum is out here, 6.4, and then the box here, the left-hand side of the box is the lower quartile. So that's the observation that's 25% of the way through the data. So you put all the data in order, and then you find the one, you go through and find the 25th percentile. So we can kind of see this if we have a look at the quakes data. If we sort by the magnitude, then we know we've got 1,000 observations, so 25% of the way through, we're going to be at row 250, which is going to be quite hard to find, I suppose. I guess we could use this indication down here. So showing row 250. Right, so this must be observation 250, so 4.3 would be the lower quartile, so which is where that edge of that box is. The median would be halfway through, so if we go down to halfway through, showing observation 500. So observation 500 has magnitude 4.6, so that's where the median line is. Then the upper quartile will be 3/4 of the way through, which will be observation 750, which is 4.9, which will be that line there. Okay, so that's what the box plot shows. So the width of the box plots here, or in this case the height of the box, I guess, is completely arbitrary. So we don't care about kind of how fat the box is. What we care about is the direction this way. So we care about where the median is a representation of centre. So again, that's a similar thing to what we had before. The centre is around 4.5, 4.6. Most of the data, so half the data, are within the quartiles, right? Because 25% are up to the first quartile, then there'll be 25% between the first quartile and the middle, which will be the second quartile, the median, the halfway point, and then another 25% between the median and the upper quartile, and then another 25% above. So you can see here that half of the data basically are between 4.3 and 4.9. And then quarter of the data are lower than 4.3 and quarter of the data are bigger than 4.3. So you can get a sense of the center, the spread, and the shape, right? You get to indicate that most of the values are to the left and there's a small tail of values out to the right. Okay? So you can basically get the same conclusions from the box plot. And 4.9. Okay, so we can tell that from a box plot as well. Okay, you've got to be a little bit careful with the box plot, and we'll see an example later on as to why we need to be a little bit careful. Essentially, we only really want to do a box plot if there's only one peak in the data. Okay, because once we've dropped the data down to just that 5-number summary, we've lost a lot of information about shape. And if we have multiple peaks, once we do a box plot, you generally infer that there's a single peak because you kind of infer that from the box. And if you've actually got multiple peaks in the original data, you only end up with one box, so it looks a bit, so your inference might be a bit wrong. So again, we can change colors. So outside with the color argument, inside with the fill argument. Okay, again, maybe not an ideal combination, but that's the idea. We'll look into when each of these should be used later on, but the one case where the box plot has an advantage over the other two is that is where you have multiple groups that you're comparing. So say you're comparing 5 different groups and you're comparing a numeric measure within each group, then placing 5 box plots beside each other allows you to very quickly assess differences in center, shape, and spread. Whereas it's hard to plot to put 5 histograms next to each other or on top of each other or something like that, and it's also hard to put 5 densities on top of each other or next to each other. It's harder to compare those shapes. So this is one reason why the box plot can be useful. But we can see a case where it's not useful when we have a look at the other variables. So let's have a look at depth of the earthquakes. So we'll grab the original histogram. So we'll do a histogram, a density, and a box plot of the depth variable. Okay, we'll see what these look like. So here's the histogram. So you can see very clearly that we have 2 peaks here, right? So we've got a bunch of earthquakes that are deep, right? So that they're around 500 or 600 meters deep. I'm guessing this is in meters, but maybe it's in, no, it must be in kilometers perhaps. And then we've got a bunch of very shallow ones, okay? So in particular, the middle of the data, the center of the data down in here, you know, the depth 300 or something, is actually where there's actually very little data. So the measure of center here, there's really actually 2 peaks. A single measure of center isn't any good, right? So the shape here is super important to indicate. The measure of center and the measure of spread by themselves give you a false sense of where the data are, right? If I said that you know, on average the depth is, you know, 300, you know, it gives you an idea as to what the average is, but actually there's actually very few earthquakes that have depth 300. Most of them have depth either very small or very large, okay? Again, the density will show us about the shape as well, so you can see that those, you know, very clearly have 2 peaks here. But when we do the box plot, right, all that information about that shape has gone away. All we know is where the middle is. So the median in this case is about at depth 250 odd, and most of the data is between 100 and, or half the data is between 100 and 540 odd. But we've got no information that there's actually 2 peaks here. Maybe we could guess it based on the width of the box or something, but you know, we really don't know what it looks like. So in this case, the box plot would be completely inappropriate. So generally, a box plot is only of use, or should only be used, if you have a single peak or hump. Right, so this is sometimes known as unimodal. So the mode would be the most common value. So if you've got multiple modes or bimodal, you've got 2 most common values, if you like. Otherwise, stick to a density or histogram. So this distribution has 2 humps. Most earthquakes are either shallow, small depth, or deep, large depth. Few are in between. So this measure of center here isn't that useful. Okay, well, what about magnitude? What about stations? Okay, so stations have a similar shape to magnitude, right? Most of them are most earthquakes are detected at a small number of stations, and there's a few that are detected at big stations. Okay, again, because there's a single peak, the box plot now is of some use. Okay, so this distribution is more skew than the others. Skew to the right, i.e. the of extreme values is out to the right. Most data is most around 25 stations. So most earthquakes have felt at around 25 stations. Right. Lastly, just to talk about these dots out here. So this is basically a property of the algorithm. So essentially what it does is it computes the length of the box and the middle of the box and the endpoints. And then it takes the length of the box and stretches it out a bit and then takes it from each end, right? So in this case, I think by default it takes the box length times 1.5 and it measures out 1.5 box lengths out here, and it kind of has a threshold that it puts out here. And then any point, any observation, any earthquake that's bigger than that, so that it's felt at more stations than about, 80 odd, in order to show that they're reasonably extreme compared to where the middle of the data are, it shows them as set points. So that's what those dots are. So these are sometimes called outliers or extreme observations. And sometimes they indicate a problem, sometimes they don't. So in this case, I don't think there's any problem at all. Some earthquakes are felt very, very widely, but most are felt not so widely. They're more localized. And that's just a property perhaps of the depth of the earthquake and the magnitude of the earthquake and things like that. Sometimes you get big gaps though. So say none of these ones were here and you just had this giant one out the end, then that could instead be a recording error, right? So maybe someone accidentally put 160 or 165 or whatever that value is instead of 65. Right, so if you just have one or two that are quite extreme, it's worth having a look at those observations to check whether it might be a data coding error or something. But otherwise, if you've got a whole bunch of them, then all it shows you is that you've got, because of that skewness, at some point, the observations are further than 1.5 times the interquartile range or the length to the box. And so that's what it does. Okay. So. Okay, so that's pretty much it. I shall upload the R sheet from this and the video now.